Hello. So now we'll study the Stokes law. First of all, this Stokes law we apply for the spherical bodies. So if there is a spherical body which is falling or going up in air or in case of liquid, we need Stokes law to calculate the viscous force acting onto this. But there are certain conditions for the Stokes law. So first condition is the body has to be spherical. It is only applicable for spherical bodies. Second condition is regarding the dimension. You see, the dimension of the spherical body with respect to the vessel, and that vessel might be the air also. So dimension of spherical body with respect to vessel should be very, very small, or the dimension of the surrounding should be very large compared to the spherical body. Meaning we'll not be using this for planets or for anything basically. It will be valid for small objects. And that to be, they have to be spherical. So if there is a spherical body and it is falling in any vessel or in air, it will experience three types of forces. Out of the three forces, two forces are driving in nature, meaning they can drive motion, and the one force is resistive in nature. So let's discuss the driving force first. So there are two driving forces which will be acting. One is mg, which will be acting at the center of mass of the body, and it will be acting downward, down towards earth, meaning I'm assuming down is the earth. And there will be Fb, buoyant force, which will be acting at the center of mass of the displaced liquid. And you see, if the density is throughout same, the center of mass of the displaced liquid will be at the center of mass of the body. So Fb will be acting upward and the mg will be acting downward. So there are these two driving forces, and the magnitude of these two forces will determine where this body will move. And based upon that, we will apply the viscous force opposite to that motion. Okay, so let's first calculate these two forces separately. So if I calculate mg, the mg will be equals to 4 by 3 pi r cube rho s. Rho s is the density of the solid. So this becomes the mass of the body multiplied with g. So that much mg will be acting downward. This is the value of mg. Now let's calculate the buoyant force. As we know, the buoyant force is equivalent to the weight of displaced liquid. And you see, the spherical body will be replacing the volume of the vessel or volume of the surrounding, which is equivalent to its own volume. So that will be equals to 4 by 3 pi r cube. That much volume will be displaced for the surrounding. In this case, I have taken that density I have taken as rho L, meaning I am assuming that to be liquid. So multiplied with rho L, that becomes the mass of the displaced liquid multiplied with g. So that much Fb is acting. So mg is acting downward, Fb is acting upward. Now let's calculate the net driving force. So if I calculate net driving force, I'm calling it Fd for a time being. So if I calculate Fd, it will be equals to either mg minus Fb or Fb minus mg. Okay? So we have to make the condition. So I'm making the condition if rho s is more than rho L. You see, 4 pi r cube is same, g is same, only difference is rho s and rho L. So if the density of the solid is more than density of the liquid, in that case net driving force will be down. So in that case, Fd will be equals to 4 by 3 pi r cube rho s minus rho L times of g. So this will be the net driving force, and that will provide us ma. A stands for acceleration. M is the mass of the body. So due to this acceleration, this body will start falling down. Now see, the moment this body starts falling down, its velocity will be downward. The moment its velocity will be downward, it will experience a viscous force. So let's discuss this side. So you see, what is happening there? For the body, acceleration is coming downward. For the body, velocity will be coming downward. And this body will experiencing the viscous force. And in the previous topic we have seen, this viscous force is generally dependent upon the relative velocity, which in this case is v. So what will happen? So after applying the viscous force, if I see the net force, after applying the viscous force, the net force will become driving force minus of viscous force. And you see, this driving force is constant. Nothing of this is going to change. Meaning density is not going to change, g will remain same, and the radius will also remain same. So Fd will remain same, driving force, but this viscous force will be a variable. because this viscous force depends upon the relative velocity, which will keep increasing. So because of the increase in viscous force, this net force will keep decreasing, net also. So now what is happening? In the beginning, acceleration is downward, velocity is downward, viscous force is upward, and net force is still downward. But with the process of time, with the time, this acceleration will decrease. Why this acceleration will decrease? Because you see, FB will increase. Since FB will increase, which will make FD, since FB will increase, which will make F net decrease, and which will make MA, acceleration, decrease. Because that was at T0. This was at T0. And this is at T is equals to T, some general time. So acceleration will decrease. If acceleration will decrease, what will happen with velocity? Velocity is not going to decrease because acceleration is decreasing, but it is still downward. So velocity is going to increase. And if velocity is going to increase, FV is further going to increase. And if FB is further going to increase, this F net is further going to decrease. This value will further decrease. And again, this chain will go on, meaning F net will further decrease, which will lead to further decrease in acceleration, which will lead to increase, but this time with a slower rate in velocity. Increase, and this will further decrease. So you see what is happening, velocity keeps increasing, but every increase in the velocity is decreasing the acceleration. So every increase in the velocity is leading towards the decrease in acceleration, which in the end will lead towards acceleration to be zero. So in the end, at t is equals to steady state. This time there will be steady state. Steady state, acceleration of the body will become zero. At that instant, net force acting onto the body will also become zero. And at that instant, whatever is the velocity, it will stop increasing. So whatever is the velocity, that will become max, and that will become terminal velocity. We call it terminal. And that is also maximum velocity, which is possible. Because you see, at this instant, acceleration becomes zero, so no further increase in the velocity will be happening. Okay? So at that instant, when that will happen, at that instant, the viscous force will be equals to 6 pi eta r Vt. That's your Stokes law, or you can say Stokes theorem. So you see, one more time. If I'm having a spherical body, and if I drop the spherical body, it will experiencing three forces, two driving and one resistive, mg, fb, and fb. So if mg is more than fb, acceleration will be downward, initial acceleration will be downward, net acceleration will still be downward, so which will lead to increase in the velocity. This fv depends upon velocity. We don't know this formula yet, and this formula is only applicable after achieving the steady state, not before that. Before that, we can only say that viscous force depends upon velocity. So if there is any increase in the velocity which will be happening, increase in the viscous force will be happening. So what happens when we calculate the net force? It becomes net driving force minus Fv. So in the beginning, acceleration is downward, velocity is also downward. So with time, velocity keeps increasing, which leads to increase in Fv, which leads to decrease in F net, and which leads to decrease in acceleration. So indirectly, you have to say any increase in velocity is leading towards decrease in acceleration. So velocity will keep increasing, which will lead to increase in viscous force, which will lead to decrease in acceleration. So based upon that, we can say in the end, ultimately, acceleration is going to be zero. So when the steady state will be achieved, acceleration will be zero, net force will also be zero. And at that instant, whatever is the velocity, that velocity will be maximum possible velocity. Because you see, at that instant, acceleration becomes zero. So velocity becomes constant. That is the max. Until that time, velocity was increasing. So at that instant, steady state velocity becomes maximum, and we call that velocity as terminal velocity. So when the velocity reaches the terminal velocity, it becomes constant. At that instant, viscous force also becomes constant. And only at that instant, the viscous force is equivalent to 6 pi eta r Vt. Only at that instant, not before that. Before that, viscous force is there. Before that, viscous force depends upon velocity. Before that, what is the formula? We don't know, we don't care. Okay? So after achieving the steady state, that becomes the viscous force. That becomes the viscous force. And after achieving the steady state, if we want to calculate that terminal velocity, we can calculate that. So after achieving after a steady state, we have a relationship, and that relationship is F net is 0. Or we can say F driving is equals to Fv. And we know the driving force. This is the driving force which is constant. So 4 by 3 pi r cube rho s minus rho l times of g is equals to 6 pi eta r Vt. See? So after achieving the steady state, viscous force achieved this value, and this was the value of driving force. So if I rearrange that equation, this Vt comes out to be, this r will neutralize this r, pi and pi will cancel out. This is 3 times and this is 2 times. So it will become 2 by 9, this 3 will come there, and 1 r and r will cancel out here. So it will be r square rho s minus rho l g divided by eta. So that becomes the value. You see, that becomes the value for terminal velocity. That becomes the value for terminal velocity after achieving the steady state. Okay. So one more time I want to explain. So there was a spherical body which was moving down because of mg. It was experiencing a buoyant force which gives the driving force this, and this is constant. So when the body starts moving down, it experiences the viscous force. And due to the viscous force, which depends upon the velocity, viscous force continuously increases, which leads to decrease in net force, which leads to decrease in acceleration, which leads to increase in velocity but with lower rate. So any increase in velocity is decreasing the acceleration. So based upon that, we can deduct that finally acceleration is going to be 0, and that becomes 0 when F net becomes 0. So at steady state, this condition follows. Whenever somebody talk about steady state, net force has to be 0, acceleration has to be 0. Along with that, the velocity becomes maximum, and that velocity is equivalent to terminal velocity after achieving the steady state. One more thing, after achieving the steady state, the viscous force also has a formula. Viscous force becomes 2 pi eta r Vt. So all these 4 things happens after achieving the steady state. So after achieving the steady state, if we need to calculate the terminal velocity, which is also the maximum velocity, if somebody will ask us, we utilize the formula Fd becomes Fb, and from there we get the velocity, terminal velocity as this much. You see? So that happens at the same time, only after achieving the steady state. All these things happen simultaneously. One more thing here we can say, if sometime that happens, the rho s is very, very, very greater than rho l. Meaning sometime when it is the air. So that happens in case of air. So sometime outside medium is the air. So in that case, we can assume the rho l to be very small. Solid density we can assume very, very high. So if that's the case, terminal velocity when we will calculate, that will become 2 r square rho s g upon 9 times of eta. You see? So that only in case of air. So if it's the air, you can decide to neglect the Fb from the very beginning. You can decide that if it is a air you are dealing with, because air will, due to the air, buoyant force will be very, very small. Okay. So this becomes the formula when it is the air, and this is the formula when it is moving in some liquid, and that's it.